Okay, we have another limit today. This one is a bit interesting, at least it doesn't look terrifying, but we might want to figure out what this limit actually is going to. So let's just look at the limits of the top and bottom. If you plug in 0 blindly, you get like something like this. The top is log 0 times log 1, right? So 0 times minus infinity, basically. This isn't rigorous, I'm just trying to gauge what this limit is about. 0 times infinity is an indeterminate form, so we can't really conclude anything about the limit of the numerator. And because of that, I'm gonna try to find what that is, the limit of the numerator. Okay, there's probably an easier way to do this question, but this is just what I came up with. Let's try to find the limit of the numerator. So maybe we write this in this way, because now we actually have a 0 over 0 situation. That's because if you plug in 0, you get log 1, which is 0, over log 0, which is minus infinity if you approach from the right, and 1 on minus infinity is basically like 0. So this is a 0 over 0 situation. Now we can use L'Hopital's rule, where we differentiate the top and bottom, and the limit should be the same as long as the new limit exists. Yeah, okay. So this would be that, and then when you differentiate 1 on log x, you get minus 1 on log squared x, or log x squared, I'm just going to write it like that, times 1 on x, because of the chain rule. Okay, great. Now, if you clean this up, you'll get like this. And now I can see this goes to 0 because x log x goes to 0 as x goes to 0. And the reason for that is, well, okay, I'll just quickly show it. You want to write this in a better form because that's not really a nice form. That's like a 0 times infinity. So if you write it in this way, you basically get log 0, which is minus infinity, over 1 on 0, which is infinity if you approach from the right. So that's an infinity over infinity case. We can do L'Hopital's rule. You'll get a 1 on x when you differentiate at the top, and at the bottom you get minus 1 on x squared. And then you can probably see when you just multiply by x squared, you get a minus x, and as x goes to 0 plus, this is clearly just going to be 0. Great, so x log x goes to 0 as x goes to 0, and that means this limit of the numerator, which we were trying to find, is just minus 2 times 0. But if you look carefully, it's because you have something like this. And this limit goes to 0, and the other limit is just 1, right? 1 on 1 plus x squared would just be 1 as x goes to 0. So clearly this thing is 0. Great, so now we know the limit of the numerator goes to is 0. And that's perfect because the bottom also goes to 0, right? X goes to 0. So we can apply L'Hopital's rule now to our original limit. So we just need to differentiate top and bottom. If you differentiate the denominator, you get 1. But as for the numerator, we get this thing. Let's try to product rule this. So we have the derivative of the first one, which would be that, times log x. And then we add, we keep log 1 plus x squared, but now we differentiate log x. So yeah. Okay, now we can just split this up into two limits. This first limit is going to be 0, right? It's pretty obvious. We have x log x going to 0. And yeah, so this whole thing will be 0. And now we just have another limit left. This one is pretty nice because it's another 0 on 0 situation. I've used L'Hopital's rule way too many times in this video. So we differentiate top and bottom. And it's clear now, this is going to be 0. And this is what our original limit was. So we can say the limit of log 1 plus x squared log x on x is 0. Thanks for watching. If you have a better solution, I'm pretty sure this is a bit convoluted. Leave it in the comments.